Welcome to Chapter 2, Section 6 in Calculus 1. We're using Stewart's 8th edition, and we're going to go through some slides that correspond to that book, and then we're going to switch over and look at a homework assignment in WebAssign. And here we're talking about limits at infinity and horizontal asymptotes. So these are different than infinite limits. Infinite limits were as x was approaching 3, for example, the y values were increasing or decreasing without bound. Here, our x value is the one that's going to be getting either really big in the positive direction, or really big in the negative direction. And that will correspond to horizontal asymptotes. And the first example we see here is where we're going to let x become arbitrarily large, positive or negative, and see what happens to the y values. And one way to do that is by looking at a table of values. So in the left-hand column, you're seeing x values that are increasing in the positive and negative direction at the same time. It just so happens that because of the function f of x, or y equals x squared minus 1 over x squared plus 1, the fact that the variable's being squared is sort of taking care of the positive and negative x values that are being plugged in. Whether you put in a positive 4 or a negative 4 and you square it, it's going to turn into a 16. So that's why the left-hand column is being consolidated, so to speak, by using these plus or minus symbols. But whether your x values are increasing in the positive or negative direction, as you keep plugging them in, you see that the corresponding y value gets closer and closer to positive 1. So whether we continue moving out to the right in the positive x direction, the y values are growing and coming up underneath the y value of positive 1, or if we go to the left in the negative x direction, as those x values get more and more negative, the y value gets larger and larger, closer and closer to that y value of 1. And this definitely is looking like y equals 1 is a horizontal asymptote. And in fact it is, and we're going to define that even more explicitly here shortly. So this is an articulation of what we were just saying, that as x gets larger in either direction, y gets closer and closer to 1, which is why we're at least initially able to say this statement. Now, this is kind of a casual conversation about defining this infinite limit, and we're going to make it more specific. So here we have what I was just calling casual. This author calls it intuitive, and our intuitive definition for a limit at infinity, this one is for positive infinity, says that as our x values get larger and larger, we can get y values that are closer and closer to capital L, which is the variable, or the letter I should say, that we've been using to represent our limit. Additional notation. This additional notation, or different notation I should say, is accompanied by some illustrations of graphs of functions that are approaching some particular y value, capital L, as x moves in the direction of positive infinity. So as we move out to the right, whether you're coming up from underneath your y value, or if you're sort of landing on top of that y value, or there are functions that will sort of oscillate above and below forever. Now this function, this rightmost function, is indeed going to continue going up and down, above and below your horizontal asymptote. However, that limit value of capital L is still considered the limit, because if we continue choosing x values that are large, we can get the y values of the function to be closer and closer to capital L. So even though it's not approaching from the top or the bottom, capital L would still be the limit, and we can still determine that limit. And even though that sort of wavier line, that third example we just saw on the previous slide, does continue crossing over that horizontal line y equals L, we're still going to call it a horizontal asymptote. More specifically, it's a y value that our function is approaching as x gets larger and larger. We're not seeing the restriction on that function that it can't cross the line, because that one does in fact cross forever, over and over. Just a commentary that we can move in the negative direction and get our y values closer and closer to +1, and the notation changes a little bit. Here we see that the limit is as x is approaching -infinity. That is accepted notation. So we went from the intuitive definition to now an actual definition, where we have the limit as x is approaching -infinity. So we've seen one for +infinity and as x goes to -infinity. Here's some illustrations of our blue curve, the graph of our function, moving off to the left and getting closer and closer to that y value of capital L, which is our limit. And here we have an actual definition of a horizontal asymptote. And a line y equals L can be considered a horizontal asymptote if the function satisfies either one of these two statements. As our x values become really large in the positive direction, if our y values continue to approach some specific y value, then y equals L is considered the horizontal asymptote. Or if we're going in the negative direction, we can say that y equals L is the horizontal asymptote. This means that third graph that we saw a few slides ago, where our curve was crossing over our line y equals L over and over again, even though the function keeps crossing it, we can still say that y equals L is a horizontal asymptote. We've thought about it for a long time as a line that our function does not cross once we move off to the right or to the left, but here we're seeing that that's not necessarily true. So just a somewhat basic example, we're seeing here two questions. This function is the same, but here our x values are going toward +infinity, here they're going toward -infinity, and we see that when you take a number like 1 and you divide it by a progressively larger number, the result is a progressively smaller number. So here we have an x value of 1 million, and the resulting y value looks like it's getting awfully close to 0. And we've seen this language many times now, that by taking x large enough or sufficiently large, we can make 1 over x as close to 0 as we please. And therefore, we can say that the limit going in either direction, whether we take 1 and divide it by an arbitrarily large positive number or negative number, the result is going to be a y value that continuously gets closer and closer to 0. So the limit is equal to 0. And since that limit, as x approaches positive or negative infinity, is equal to 0, we can say that y equals 0 is a horizontal asymptote. Did we need to satisfy both of these statements in order to say that y equals 0, or the x-axis, is a horizontal asymptote? And the answer is no. We only had to satisfy one of them. In fact, we're going to see an example here shortly where as you move in the positive direction, your y values approach one number, and as you move in the negative direction, your y values will approach a different value. So we'll have two horizontal asymptotes. In the example we just looked at, 1 was being divided by x, or x to the first power. But here we're seeing a theorem which we can use as law that says that if our x value is moving in the positive or negative direction, off toward positive or negative infinity, and we're taking a constant value, 1, and dividing it by x to the power of a rational number that's greater than 0, then the limit will equal 0. We don't have to go through the process of proving that for every function that we deal with. This is going to be a nice tool for us. A rational number, remember, is a fractional value. A number that can be expressed as a fraction is a rational number. Like 1/3, which is an infinite decimal, but it's an infinite repeating decimal, 0.3333, and so on. 1/7, I believe, is 0.1444444, so even though it goes on forever, it's repeating. A number like pi, however, while the decimal goes on forever, there's no repetition in the actual decimal. So pi is considered an irrational number because it cannot be expressed as a fraction. It can be approximated as a fraction, but it cannot actually precisely be represented as a fraction. So again, rational number is a fractional number. And here's our next example. We're supposed to be evaluating the limit as x goes to positive infinity as applied to this function. We've got a polynomial in the numerator and a polynomial in the denominator. You're welcome to read all of this, but I'm going to tell you that our next step in order to evaluate this, because if you thought about this from direct substitution, which is pretty much what this text says, your numerator and your denominator would both become exceptionally large as your x value went toward positive infinity. So what's the strategy that we use in order to pretty formally prove or demonstrate that the limit of this function is equal to whatever it's equal to? How do we find it in a very legitimate way? And the answer is we take the numerator and denominator of our original function and we divide by the variable in the denominator that's being raised to the largest power. So in this case, the denominator contains an x to the power of 2. 2 is the largest exponent we're seeing down there. So we're going to divide the numerator and denominator by x squared. Effectively, what we're doing is taking our original function and multiplying it by 1 over x squared over 1 over x squared. And that fraction is equal to 1. So we're really multiplying by 1, which doesn't change the value of our function at all. It's just changing what it looks like. So that's why we're allowed to do that. And then, if we distribute our division to all 3 terms in the numerator and all 3 terms in the denominator, the 3x squared over x squared would cancel there. The x over x squared here would reduce to 1 over x. The 2 over x squared can't reduce, so we're left with 2 over x squared. In the denominator, 5x squared over x squared. The x squareds would cancel, leaving us just with the 5. 4x over x squared reduces to 4 over x. And the 1 is divided by the x squared. Can't simplify that at all, so we're left with a 1 over x squared in the denominator. Why did we do that? Because now, using properties of limits that we've already seen, we can take the limit that's being applied to this rational function, fractional function. We can distribute the limit statement into the numerator and the denominator, and then we can distribute the numerator to each of the terms in the numerator and each of the terms in the denominator, and evaluate each one of those limits independently. So here's that first step. By limit law 5, we're distributing to the numerator and denominator, and then by limit laws 1 through 3, we've distributed over addition. we've distributed over subtraction, and there was this multiple of 2 in the numerator of this fraction, and you see that it's not here anymore, and that's because we factored it out. I believe that was limit law 3. So we've utilized all of those, and now we're going to evaluate these limits. We've got the limit of a constant, we've got the limit of, now we're up to speed, right? Here's the limit as x goes to infinity of 1 over x, and that was one of the first examples we saw in this lesson. And then the next term is 1 over x squared, which is 1 over x to the r, where r is a rational number, and 2 can be expressed as a fraction, 2 over 1. So that satisfies the requirements for us to be able to utilize that theorem, and we can apply those 3 properties or limit laws or theorems in the denominator also. 3 remains a 3, no matter how large we make our x value. And similarly, 5 stays a 5, no matter how big x gets. But 1 over x, as we saw, when you make your denominator extraordinarily large, this fraction is going to equal 0. The same thing applies here, so that this entire limit becomes a 0, and 2 times 0 is going to be 0. Same thought process in the denominator. This limit evaluates to 0 times 4, 0, and 1 over x squared. That limit also evaluates to 0, leaving us with this bit of arithmetic and a final answer of 3/5. Some of you may go on to a Calculus 2 class or further and be asked to actually write out this process. You might have to demonstrate this in great detail. It depends on who your professor is. In a homework assignment, you might be asked to fill in certain blanks by whatever software you're using in order to demonstrate your understanding of this process. So while there is a shortcut, and then even later we're going to learn another shortcut, it's good that you understand that there are these limit laws that are going on behind the scenes in order to have us very legitimately arrive at a solution for this particular problem of 3/5. If we were to go through the motions and sort of tear apart our original rational function like this, except instead of x going to positive infinity, if we sent it off to negative infinity, we would see that the same result is reached, that your y values or your limit would be approaching positive 3/5. And here's an illustration of that. You can see that as we go off to the right, our y values are increasing and approaching that y value of 3/5, whereas we go off to the left, our y values are actually coming down from above a value of 3/5, but still approaching that value of 3/5, or 0.6. And here we have the same task of finding the horizontal asymptote, or asymptotes, perhaps. We're also being asked here for the vertical asymptote. And because our factor in our denominator of 3x minus 5 cannot be canceled out with a identical factor in the numerator, then 3x minus 5 is a non-removable discontinuity, and it's going to manifest graphically as a vertical asymptote, and that vertical asymptote will happen when this factor in the denominator equals 0. So we can find the vertical asymptote simply by setting 3x minus 5 equal to 0 and solving for x. The more challenging part, as we become acquainted with different scenarios where we're asked to find a horizontal asymptote, the more challenging part of this one is to figure out how am I supposed to sort of tear this rational function into the smaller pieces so that I can distribute my limit statement. And this one's not too difficult to wrap your mind around, I don't think. we're still going to use that initial strategy or first step of dividing the numerator and denominator by the variable that's in the denominator being raised to the largest power. So let's look in our original denominator at the top of the screen, and I see a 3x to the first power. That's the largest exponent applied to our variable in the denominator, so that's what we're going to divide by on the top and the bottom. So here's our numerator being divided by x, our denominator being divided by x. And then surely we could distribute our division in the denominator. 3x will be divided by x, and the 5 will be divided by x, or negative 5. But in the numerator, how am I supposed to get that division by x into my square root symbol? And the answer is, we're going to express this x as the square root of x squared. And that way we'll be able to incorporate it into the numerator. And here you can see that it has now been incorporated into this larger square root symbol. A square root of a fraction could be written as the square root of the numerator divided by the square root of the denominator, except here we've done that process in reverse. We expressed our denominator as a square root so that we could reverse this process and turn it into one large square root covering our entire fraction. And what that allows us to do is distribute this division under the radical. The 2x squared will get divided by x squared, the positive 1 will get divided by x squared, and of course when 2x squared gets divided by x squared, the x squareds will cancel. Looking down to the next line, we're left with just the 2, but to the right of that 2 we see this 1 over x squared because we could not simplify that. In the denominator, we're distributing our division as well. The 3x divided by x reduces to just a 3, and this subtraction by 5 gets divided by x, can't simplify it, and so we still have the 5 divided by x. And now we can finally use our limit laws and distribute this limit into all of the terms that we're seeing, both in the numerator and denominator. And once we do all of that distribution, first into the numerator and denominator, and then into all of the terms in the numerator and denominator, we can finally evaluate those individual limits. And we're seeing again from this section the 1 over x squared and the 1 over x, both of those going to 0, which makes this 5 turn into a 0 when it multiplies by the 0. And so all we have left are these constant values. That's all that lingers, but in the numerator our square root symbol is still there, which is why our final answer moves from here onto the next slide, and we see it as the square root of 2 over 3. And that is our horizontal asymptote. Now all of these limits were as x was going off toward positive infinity. We did not investigate x going to negative infinity. But if you glance back up to, let me get rid of some of these marks, there we go. If you look back at this statement, right before we applied the limit, and you send x to negative infinity instead of positive infinity, you'll see that these two rational functions, both of those, when you apply the limit, you would get a 0 value also when you send x to negative infinity. So you would get the same limit as x goes to negative infinity. Your limit would be the square root of 2 over 3. But there is a little hiccup that we run into here, because when you send x to negative infinity, and then you have to, or if you then encounter the square root of x squared, this is it's a little tricky, because the squaring and the square rooting should cancel each other out. And you've learned this in a college algebra class perhaps, that when your index, it's a square root, so it's a second root, matches up with your exponent inside the radical, and there's another 2, that when those cancel out, so to speak, you do have to put the argument inside of an absolute value. So what you're seeing here is the absolute value of x. And then you see another equal sign equals negative x. Now why would that be? When I take an absolute value, I should get a positive number, right? That doesn't look like a positive number, except it is. Because what's happening right there is we are negating an x value that's negative. So that double negative would turn it into a positive. So let's have a look. This is just the numerator from our previous process, a couple slides up. That's just the numerator, and we divided the numerator by x, and then here's that change that we made, where we said, well, let's write x as the square root of x squared. And then here's the sort of little hiccup, is that because we're sending x to a negative infinity, because x is going to be a negative value, and because of this conversation that we just had up here, when we make this substitution, so to speak, we have to introduce this negative sign in front of the radical. And that negative sign is going to hang with us. Now it's out in front of the radical. It's still in front of the radical. And then when we incorporate it into the numerator of that original function, and then we start applying limits, this negative sign is still with us. Now, there weren't any differences in our processing of the denominator as we sent x to negative infinity. It was only the numerator that got a little weird, and that was because we were square rooting a square of a negative value. And that's what caused us to have to introduce this additional negative, if I can say it that way. And the result, as you're seeing at the bottom of the screen here, is that the horizontal asymptote, the limit that we approach as we send x to negative infinity, is indeed not positive root 2 over 3, but negative root 2 over 3. And that is something that you're not going to run into frequently. However, it is out there and is definitely something that could be thrown at you to try to trip you up, or just to give you the opportunity to demonstrate your in-depth knowledge of this limit process and the limit laws and some of the algebra that's also still going on as part of that process. And so this function actually has two horizontal asymptotes, y equals positive root 2 over 3 and y equals negative root 2 over 3. And here's that last little comment about the vertical asymptote. Our original denominator was equal to 0 when x equals 5/3. As we approach 5/3 from the right with x values that are larger than 5/3, the denominator is awfully close to 0 but stays positive. And so our y values would be curving up toward positive infinity as we approach an x value of 5/3 from the right. And the numerator is always positive, so thus we can say that as we approach an x value of 5/3 from the right, this function is going to have a y value that approaches positive infinity. Now, as our x values approach 5/3 from the left, we have to be careful, because the denominator is going to remain ever so slightly negative as we approach a y value of 5/3 from the left. Because this x value is less than 5/3, when you multiply it by 3, this term is going to be slightly less than 5. And then when we subtract 5, we're going to have just a little baby negative number. Very small, but still negative. The numerator, however, is still going to be a positive number, and so when we take that numerator that's a positive number and we divide it by a little baby negative number, the result is going to be a really big negative number. We'll be heading off toward negative infinity. And so here you see the graph for this function. As we're coming in toward an x value of 5/3 from the right, our curve is going up toward positive infinity. As the blue curve comes in toward x equals positive 5/3 from the left, it dives down toward negative infinity. So we do still have an asymptote there. It just so happens that our function is going opposite directions depending on whether we're coming in from the left or from the right. And you see those magenta horizontal lines, y equals positive and negative √2/3. Those are our asymptotes. Pretty interesting behavior on this graph. As we go off toward the right, our blue curve looks like it's going to land on that magenta line. Of course, it never actually touches it, but that looks like what's about to happen. But as we head off to the left, this blue curve comes up and crosses over its own asymptote first, before then coming down and settling toward that y value on the high side. Interesting stuff. A lot of variety that you can run into, so you've got to keep your wits about you. Keep both eyes open. Infinite limits at infinity. It's not a double negative, it's a double infinity. And the notation that we see for all four of those instances or scenarios are listed here. As you go off to the right, your y values could be approaching positive infinity, or as you go off to the right, your y values could approach negative infinity. However, as you go to the left toward negative infinity, your y values could get really large, or as you go off to the right, your y values could get really large in the negative direction. So those are your infinite limits at infinity. What do some of those look like? Here's one of them. You're taking a positive number that's heading off toward positive infinity, and you're raising it to an odd power, and so that will still yield a very large but positive number. Now in the second case, as we're heading off toward negative infinity, we're taking a very large negative number and raising it to an odd power, and a negative to an odd power will yield a negative number, and in this case it's going to be a very big negative number. So as we again head off toward positive infinity, the y values will get really large in the positive direction, but as we head off to negative infinity, our y values will get really large in the negative direction. And there's the graph of x cubed, which you know pretty well. It's one of our parent functions that we first learn about in the algebras as we're learning about functions. This is also an odd function, which is symmetric about the origin. Just a little throwback there for you. And we've made it to slide 32, where we finally get to start talking about precise definitions. And here we're seeing our epsilon again. We're not seeing delta. We could incorporate delta by subtracting capital N from both sides, but in this case we're going to leave out the delta and say this a little bit more forwardly, I suppose. So let's look at this statement. As our x values head toward positive infinity, our function looks like it's going to have y values that are approaching capital L. And whatever that y value is that we're approaching, we're calling that the limit. Capital L is that y value. And what does that mean? It means that for every epsilon value greater than 0, there's a corresponding number n such that these two things. Okay, let's translate these one more time. Doesn't hurt to revisit the interpretation of this kind of notation. The unknown that we most frequently work with, it used to be delta, but in this case it's going to be capital N. And it's that capital N that's going to help us achieve a particular goal. And what is the goal? The goal is this. We want to get the y values of our function to be within epsilon of our limit value. Remember, we want to be constraining our y values. We want to make our target smaller and smaller around that capital L value, that y value. And how do we make that happen? In this case, we make that happen by making our x values larger than, and then that's what we have to figure out, some particular n value. Now, there are going to be times where you'll calculate n and it will be a number, but usually what we do, as we've gotten farther along in our discussions about these precise definitions of limits, is that the n value, and previously the delta value, was actually defined or determined in terms of epsilon, so that as the constraints of epsilon got smaller, the delta value, or in this case the n value, would just sort of naturally follow suit, and that constraint would get more and more specific in terms of epsilon. I like looking at it graphically, so graphically it says that by keeping our x value large enough, larger than some value n, our y values will stay within L plus or minus epsilon. So our f values need to land in here, and how are we going to make that happen? By keeping our x values bigger than n. And if we can establish or figure out some kind of a relationship that makes this happen, no matter how small this plus or minus epsilon gets, no matter how small epsilon is, if we can still find an n value that will push us out here and keep us within that plus or minus region, then we are allowed to say that our limit for our function as x goes to positive infinity equals L. A similar definition applies to a limit as x heads toward negative infinity. The only difference here is x is going to negative infinity, and we're keeping our x values smaller than some n value. And this n value, no doubt, is going to be left of 0. We're into the negatives. But here we still have that plus or minus epsilon, because our target in the y direction is still being refined. We're just going to make sure we hit that target by choosing a x value that's farther and farther to the left, or more and more negative. So let's use the definition in order to prove that this limit is equal to 0. So we're given an epsilon value that's greater than 0. They're not telling us what it is, which is very rude. They're just keeping that to themselves. However, we're being told that epsilon is greater than 0, and that we need to find an n value such that if we can find an n value that forces our x values to be larger and larger, then the difference between our, or I should say, our y values will be within epsilon of our supposed limit, capital L, which is 0. There it is. That 0, that capital L. Okay, so how do we do that? Have a look at this statement right here. This is about our y values and involves epsilon and our capital L value, right? Epsilon is in the y direction. 0 is our limit, which is a y value. And this is our function, which when you put in x values, generates y values, okay? So here's our statement about y values. And let's clean this statement up a little bit. What's 1 over x minus 0? Well, that's still 1 over x. Great. And what's the then, we don't need that 0 anymore, what's the absolute value of 1 over x? Can I get rid of those absolute value bars? You might be thinking, no, you don't want to do that because what if x is negative? Dude, x is on its way toward positive infinity. I don't think we have to worry about x being negative, not in this scenario. So we can let go of the absolute value bars also, and what we have left is just 1 over x is less than epsilon. So let's take that now and write it down over here. There it is, 1 over x is less than epsilon. Now what? Now we're going to take the reciprocal of both sides of that inequality. Or you could sort of cross-multiply your way, but anyway, or raise both sides to the negative first power. But the reciprocal of 1 over x is just x, and the reciprocal of epsilon is 1 over epsilon. And so our previous y statement, a statement about our y values, has now evolved into this. And as you might recall from our previous conversations about trying to figure out what the heck our delta value is, now we're trying to figure out what's our capital N value. And the way that we made that happen, or figured it out when we were working with delta values, was we modified our y values statement, our epsilon statement, until it matched up pretty well with our delta statement. And if you'll notice, please compare and contrast this statement to this statement. See the x, see the x, see the greater than, see the greater than. Guess what we're going to let n equal? How about 1 over epsilon? There they are. N is going to be 1 over epsilon, and the author agrees with us. I love it when that happens. Let's choose n to equal 1 over epsilon. So if you were asked, in order to prove this statement, you can prove that statement by demonstrating your ability to find an n value such that no matter how small we make epsilon, if epsilon is small, what's 1 over epsilon? It's big, which means our n value gets bigger as our epsilon value gets smaller. So what we've shown is that we can find an n value sufficiently large that no matter how small you make epsilon, we're going to give you immediately, instantaneously, give me an epsilon value. 0.000001, great, I've got an n value for it. 1 divided by 0.000001 is the n value that's going to keep our x values large enough that it's going to allow us to hit our target, which is only 0.000001 away from our capital L value, our limit of 0. And since we can find this specific relationship, we are allowed to make conclusively this statement, that the limit is 0. You should feel very proud of yourself. Coming to terms with that relationship between epsilon and delta, or between epsilon and capital N, is a difficult task. Conceptually, it's very strange. We found something, but we didn't really find something. What we found is a relationship between epsilon and delta, or epsilon and capital N, in order to prove that no matter how small we make epsilon, we just take that epsilon value and put it into our new little formula, and that cranks out an n value that's extraordinarily large, allowing us to hit an extraordinarily small target. These conversations that relate to infinity are kind of mind-bending. So you're doing great, hanging in there, keep at it. This is an illustration of where we have an epsilon value, of 1, And what's the reciprocal of 1? It's 1. So our n value would be 1. And what that does is it says that as long as we're using a n value that's larger than 1, our function values will be within 0 plus or minus 1. And sure enough, the function is within that domain or range. And then we go on and we say, well, let's make epsilon even smaller. Let's make it 0.2. What's the reciprocal of 0.2? Or 1 divided by 0.2? Well, that's 5. Okay. What happens if we look at our function values where our x coordinates are larger than 5? Well, the y values will still be within 0 plus or minus epsilon. And there they are. They've been drawn in magenta for us there. So we've refined the target and made the target even smaller. So we had to pick a larger n value. And sure enough, as long as we stay above that n value with our x coordinates, the y coordinates will be within our target. And then one step further, epsilon is 0.1, now n is 10, and our magenta part of our curve continues off to the right, and it stays within the acceptable plus or minus above and below our limit value of 0. 0 plus or minus 0.1. So no matter how small that epsilon value would get, the n value would resultantly get larger and larger, keeping our magenta part of our curve within 0 plus or minus epsilon. And then we have infinite limits at infinity, so it can happen that as your x values get really big, your y values get out of control in the positive direction. That can happen. We can very specifically say that that kind of a relationship is true if our y values are meant to be larger than some arbitrarily large m value. Then all we have to do is find an n value as sort of a lower limit so that we keep our, as long as our x values are larger than n, our y values will be larger than m. And if we continue pushing that concept off to the right farther and farther toward positive infinity, our y values will just keep growing. And that's an indicator that our limit is equal to positive infinity. That can happen in the negative direction also. You could move your x values toward positive infinity and your y values could go diving down toward negative infinity. That's possible. Or if you go off to the left and you have a limit as x approaches negative infinity, your y values could curve up toward positive infinity or be diving down toward negative infinity. All four possibilities exist there also. We are at the 48-minute mark. Props for hanging in there. I'm going to let's do it. Let's just stay here and switch over and have a look at some homework. These are some more example problems that you might run into. We've covered most of our bases on these. You're going to use this graph in order to evaluate these limits as it goes off to the right toward positive infinity. What's happening to our y values as we go off to the right? Looks like the y values are approaching a y value of -2 because here's our x-axis where y is equal to 0. So use that graph in order to make some conclusions about what your y values are doing as your x values are approaching these various numbers. Now those are all limits. So in order to answer this, for example, the limit from the left must equal the limit from the right. If it doesn't, then that limit's undefined. The equation of a vertical line will have an equation that looks like x equals some number. A horizontal line has an equation y equals some number. You've done problems like this before where you're given some sort of constraints and you need to match it up with the correct graph. I would use that same approach. Which one of these four graphs down here satisfies each one of these limit conditions. Just march through and keep comparing them to the graph. As I approach an x value of positive 1, for example, does my graph dive down toward negative infinity? Well, let's look at the first graph. Here's an x value of positive 1. That's this vertical asymptote. Is my graph diving down toward negative infinity? Well, if I look at it, if I'm coming in from the right, it dives down toward negative infinity. But if I come into an x value of positive 1 from the left, it goes up toward positive infinity. Does positive infinity equal negative infinity? No, it does not. Therefore, in this graph, you would say that that limit as x approaches positive 1 does not exist. Okay? It has to be approaching from the left and from the right. It's got to be heading toward the same direction in order to make a statement like this. So at x equals positive 1, your graph better be curving down, there we are, from the left and from the right. Both of those have to be satisfied. So keep marching your way through those limits until you've figured out which graph gives you the correct representation. Excuse me. Problem number 3. Talking for 50 minutes makes me a little scratchy. Problem number 3, we saw a problem like this earlier in the video. This is a rational function. You need to divide the numerator and denominator by your variable to the largest power. So you'll be dividing by x in the numerator and denominator. Don't forget to distribute your division to all terms. Problem number 4, same idea. Dividing numerator and denominator, in this case, by x squared. And be careful, your x value is going toward negative infinity in that problem. I don't see any square roots of x squared in that problem, so you don't have to watch out for that little challenge. But it is going toward negative infinity, so be careful when you start evaluating your limits. Here, find this limit as it exists. What are we going to do? Same approach. Divide your numerator and denominator by t squared. If I were you, I would represent this as t to the 1/2 power. And remember that if you have a variable to a power divided by the same variable to a different power, that this is equal to the upper exponent minus the lower exponent. So if you're dividing t to the 1/2 by t to the 2, you'll have a little bit of arithmetic to do there in order to find your new exponent. And then refer back to that theorem that we saw, where you have the limit as your variable is approaching positive or negative infinity of 1 over your variable to the rational exponent. Okay, we were told that this equals something very specific. If you don't remember it, go back through the video, it's in there. It's one of our theorems, I believe it was called. Here we have to find the limit as if it exists, and here, same approach. You're going to divide the numerator and denominator by that variable to the largest power, except in this problem you're going to have to incorporate it into this square root. So your numerator will be, the first step of it, we'll say 4x to the 6 minus x divided by x to the third. That's the same thing as that square root divided by the square root of x to the 6. Okay, x to the third and x to the 6 square rooted are equivalent. And that will allow you to write this as 1 square root over your whole fraction, 4x to the 6 minus x over x to the 6, and then you can start distributing your division and then eventually distributing your limit. We saw an example like this earlier in the video, so please refer back to the steps that were present there. Number 7 is different than anything we've seen thus far, and this one is tricky. I'm going to leave you to do the arithmetic, but I'll tell you what to do. You're going to take this expression, this whole thing, and you're going to multiply it by, and you can think of it as being over 1 if that helps you. You're going to multiply it by the conjugate divided by itself. you're going to multiply by a fraction right here that's equal to 1. So we're multiplying by 1, which won't change the value of it, but it's going to change what it looks like. You're going to multiply by the square root of 16x squared plus x plus 4x over the exact same stuff, 16x squared plus x plus 4x. I told you this fraction is equal to 1. Anything divided by itself is equal to 1. Multiplying by 1 doesn't change the value of our original statement, just changes what it looks like. Now you're going to need to FOIL this numerator times this numerator. Combine like terms. The O and the I terms should cancel each other out. When you FOIL conjugates, the O and the I terms should cancel each other out. So do some FOILing, combine like terms, simplify up there, and then have a look at your new fraction. And then you should be able to use the laws and properties and theorems that we've seen so far in this section, and you should be able to continue progressing through the rest of the solution process. If indeed the next step that you choose to use is dividing numerator and denominator by the variable that's being raised to the largest power, that's the one that you'll use, x to the first power, because this is the square root of x squared. So really dividing by x to the first power, that's still as big as it gets in your denominator. This is another scenario that we had not run into until just now. The strategy here is factoring out the variable to the largest power. So this turns into the limit as x goes to negative infinity in this case of, I'm factoring out an x to the fifth, or dividing it out, if that helps you. And what is x to the 4 divided by x to the 5? Well, you could either call that x to the negative 1, or you can call it 1 over x. So let's write this as 1 over x plus 1, and we can always make sure that we factored correctly by distributing and checking to make sure that we get back to our original statement, and if you multiply that out, you will get this original expression. And now that we've factored that out, you have this factor times this factor, and by the properties of limits, or our limit laws, the limit of a product is equal to the product of the limits, as long as we're not going to accidentally divide by 0. And there's no danger of division by 0 here because we're sending x to negative infinity. So distribute your limit to these two factors, then evaluate each of those limits and see what you get for a final answer. The limit of a product equals the product of the limits. In number 9, we're sending x to positive infinity for arctan. You should take the initiative to refamiliarize yourself with the graph of the arctan function, or inverse tangent function. Refresh your memory on the domain and the range of the inverse tan function. And remember that e is a number. E is, I think it's approximately 2.8 or 2.7. So it's a number that's larger than 1, and you're raising it to a really big power. So this inner function, e to the x, is getting really big. So now you're taking the arctan of a huge number. Have a look at it graphically, and I think you'll find the solution presents itself pretty quickly. What y value is that arctan function approaching? Finding horizontal and vertical asymptotes for this curve. The vertical asymptotes for this function happen when the denominator equals 0. So you will need to find the zeros of this denominator. You might consider factoring by the AC method. You should be able to find a separate video about the AC method. I don't think I have one that specifically targets it. One of my algebra videos surely contains that method. If I noted it in the timestamps, maybe you'll find it on my channel, otherwise you should be able to find it somewhere else. And the numerator does not factor because it's the sum of squares. The difference of squares factors, but the sum of squares does not, so don't try to factor that. And the horizontal asymptotes, you're going to use the same strategy that we've been using so far, which is to divide numerator and denominator by the variable to the largest power, in this case x squared. So divide numerator and denominator by x squared, and then evaluate your limit as it goes to positive infinity, and consider evaluating your limit as it goes to negative infinity. Make sure that you don't have two horizontal asymptotes. Trying to get number 11 on the screen entirely here. We're finding a formula for a function that has vertical asymptotes at those two x values, and what that means is that you need factors in the denominator that would turn into a 0 if you plugged in those two values. So that's what causes vertical asymptotes. And a horizontal asymptote, if you took this denominator and you multiplied it out, you would end up with x squared plus some other stuff plus a number, right? So you'd have three terms down there. But my point is that you'd have an x squared in your denominator. And if you want a horizontal asymptote of 1, then when you divide your numerator and denominator both by x squared, the result after you apply the limit is going to need to equal 1. So what I'd like you to do is use your process of having figured out the horizontal asymptote for this problem. Use your process for figuring out the horizontal asymptote for this problem, number 3, and use those as models in order to try to figure out your own function for problem number 11, so that you have these factors in the denominator that cause your vertical asymptotes, but use those other previous problems in order to help you achieve a horizontal asymptote of y equals 1, or whatever your number turns out to be in this problem. And then number 12 is a nice conceptual problem. If you have a polynomial over polynomial which creates your rational function, then if the degree of your numerator is less than the degree of your denominator, see if you've picked up on any patterns as far as what the resulting horizontal asymptote or limit will be. And then part B, I really like part A. Part B is equally as valuable but a little less specific. What if the degree of your numerator is the larger of the two? What could you safely say about the horizontal asymptote, or the limit is what you're specifically being asked about here, if the degree of your numerator is larger? And those, is there more? I didn't think so. Okay. Those are some really great starting scenarios, and it gives you some good concepts to wrestle with. There's a lot of really good examples in here. Take notes on these notes, whether you have found the printable PowerPoint slides and you're filling those in, or if you're not doing that. Either way, I would say it would be a really good idea for you to make a list of, or flashcards with, these different scenarios and what the first couple of steps in the solution process are. For example, if you have a rational function, how do you start evaluating that limit to find the horizontal asymptotes? And then there are subcategories to that. What if your rational function has a square root in the numerator? What if your rational function has a polynomial over a polynomial where the degree of the numerator is larger, or the degree of the denominator is larger, or the degrees are the same? Are you seeing patterns there And can you maybe eliminate a lot of your work and already know what the final answer is going to be? Or should you include some notes as pertain to those certain circumstances about how to get those problems started, what some of the tricks are? For example, if you have to take the square root of x squared while you're sending x to negative infinity, make sure that you're mindful of that as one of the maybe most unusual things that you could run into that we've talked about in this section. All right, there was a lot of stuff in here, a lot of different scenarios. Get them organized, and I will see you in the next section.